Welcome to the viewers. Today we discuss this idea of relationship between the separation axiom in topological spaces. At first we are starting with that every T2 space imply T1 and converse is not true, and every T1 space is imply T0, and here converse is also not true. Then how to prove it? At first we are going to the first problem. For T2 space, let x tau be a topological space with tau as topology already mentioned, and for T2 space, and tau is given by phi x, and there is open set A and B if we consider, and we define as space as the elements like this, like A B in this way, A B, and this type two element we consider. And clearly by definition of T2 space or Hausdorff space, the two distinct member like this A and B, here A is not equals to B, and we find A and B, and if there exists some of the open set containing A, if AB belongs to topological space, and if A belongs to the element like the set U, and B belongs to the element like the set V with U intersection V, that will be equals to phi. This is our main concept. AB are distinct point of X, and there is an open set U containing A, another open set B, where U and V are open set contain point or member A and B in X. We find it this is the topological conditions, and this is a condition of T2 space. So here x tau is T2, and if we consider this element containing each one of them, suppose U contain the element, each element A without B, since U contain A, one of them containing one of them without B, and that is open set, and open set V contain B, that means V contain B without A, so it is T1. That means so x tau is T1 also, that is T2 imply T1. But if we consider X be an infinite set, and here is another concept like this G be an element, infinite set, and G be an element like capital G, if we consider is a subset of X in such a way that X minus G is finite, that may be empty, then this X and cursive G forms a topology, and this is cofinite topology. We already know, but here is our object, that this is a T1 space we have to prove. At first, if we consider x1, x2 be the element in the space X with x1 is not equals to x2, then we find this system U is equal to x minus x1 and V that is will be x minus x2, and there is a member containing U and V respectively. So x1 is outside U and x2 is outside V. So x cursive G is T1, but it is not T2. Separation. It is not T2 separation. But how these things happen? If two open sets, that means two open set, if we say like H1 and H2 in X, such that arbitrary element, whatever may be the member is, that will be absolutely arbitrary. We have different type of choice, no matter for that. Here we take like X belongs to H1 and Y belongs to H2 with this H1 intersection H2, that will be phi. Then that will be given in the spaces, so it will form the property of the cofinite topology like this: x minus h1 and x minus h2. So x minus h1 and x minus h2 are each finite subsets of x. So their union x minus h1 union x minus h2 is finite subset of x, that is h minus h1 intersection h2 by De Morgan's law is also finite subset, but it is phi, that is h minus phi is finite subset. That is h is finite. A contradiction. So here we get x finite, but we assume here by cofinite topology x is infinite. So there will be the contradiction. Here we consider x as infinite subset. If we assuming with this type of property, if there will be the T1 separation, T2 separation, then and we maintain this type of criteria like this, there will be no intersection, and if we applying this property we get x is finite. We consider here x is infinite. Here we finally find if there will be T2 separation, x will be finite. So there will certainly not T2 separation. So only we find x1 is T1 separation. So we can say that T2 imply T1, but converse is not true, hence the proof. So we get some of the idea about this, and this video is too long, and the next videos we prove that T1 imply T0, but T0 does not imply T1. We end our discussion today. If you like this video, like it, share it, and don't forget to subscribe the channel. Thanks for watching.